Let's first talk about the interstellar medium in our galaxy. And here is one of the pretty pictures from Hubble that shows a reasonably typical combination of interstellar clouds. So simply, it is the gas and dust between stars. Yeah. And it is generally mostly concentrated in a galactic disk, but not entirely. And it's stuff from which stars are made, or galaxies for that matter. All of the baryons in the universe, protons, neutrons, and electrons that go along with them, were originally in form of a gas. And now we think that, in fact, maybe 90% of all ordinary matter in the universe is in form of gas, not stars. So stars are in sort of an ecological equilibrium with interstellar medium. They form from interstellar medium, from gas clouds that condense. We'll talk about that in a moment. They live their lives, then some of them explode, others lose their envelopes, and thus they contribute back to the interstellar medium. But the material that comes out of them was enriched by heavier chemical elements that were cooked up in stars. And then new stars form. Stars also interact with interstellar medium. They can change it, they can ionize it, they can be mechanical effects of shock waves. And so it's a fairly complex system. And there isn't a continuum of properties, but it does fall into several different categories that I'll define in a moment. So there are three basic forms of interstellar gas that are associated at least with the galactic disk. First, young stars emit lots of UV radiation, and that means they will pump up internal energy levels of atoms or ions to higher energies, which occasionally they will lose electrons, and they will recombine, and when they do this, they shine in emission lines. You'll see the red color tends to go with these, and anybody has a guess, what is the spectroscopic line that dominates this? Let's try this way. What chemical element is it likely to be from? Yes, hydrogen. And so anybody cares to guess what's the spectroscopic line? Which line series of hydrogen is in the visible part of the spectrum? Balmer series, that's right. And the strongest of those will be the first line, alpha. So this is H alpha, as it's called. There are others, of course. But that's what tends to carry most of the energy in these recombination nebulae, at least in the visible part of the spectrum. And that's what gives them this reddish color. What about the blue stuff? You think that's also ionized gas? Well, sometimes a little bit, but mostly that's just starlight reflected from interstellar dust. Now, you don't think of dust as a mirror or a lot of little dust grains, but they will reflect some fraction of photons that come upon them. And the reason why it tends to look blue is that among young stars, the most luminous ones are the hottest ones. And thus, most of the starlight in the vicinity of star-forming regions tend to be dominated by very blue continuum light, so you see a reflection of it, of dust clouds. And then there are dust clouds, which usually appear as shadows on the optical picture, hiding stuff behind them. But if you were to take a look in far infrared, you will see them shining bright in thermal infrared. They absorb visible light from starlight. Then they get heated up to temperatures of tens, sometimes a couple hundred degrees Kelvin, but usually it's tens. And they emit in mid to far infrared. You probably remember Wien's law, which connects temperature with the peak wavelength. So for solar type radiation, temperature of sun is 6,000 degrees, roughly speaking. Where does the spectrum peak? Around which wavelength? You have eyes that see in the visible part of the spectrum, And so what could it possibly be? Yeah? Well, yeah, very smart. Now where exactly? Well, kind of in the middle. It's more like yellowish light. It's about 5,500 angstroms. Okay, so the sun is 6,000 degrees, and let's say interstellar dust cloud is 60 degrees Kelvin. What would be the peak wavelength of that? Starting with, say, 500 nanometers. Well, I'll let you figure this one out for yourselves, but it will be in far infrared, maybe even sub-millimeter regime. So I said that there are several different components. Two of them were captured in that picture, the cold and the warm gas. Cold gas and dust tend to be these temperatures of some tens of Kelvin. Molecules tend to be well mixed with dust grains, and only small fraction of all volume, but maybe a lot of mass, is contained inside these cold clouds. They're all exclusively in the thin disk of the Milky Way, and that's where stars are formed. They're obviously not well ionized because they're cold, and their primary importance is that this is what stars are made from. Stars are made exclusively from cold interstellar gas and dust. Warm is the one that makes pretty pictures. It is the ionized gas, mostly hydrogen, has temperatures of some thousands of degrees, typically maybe around 10,000 degrees Kelvin, and a lot of it is ionized, not necessarily all, and it shines in these nice recombination lines. So that tends to fill most of the volume around clouds of the cold gas. And then there is a hot component that you didn't see in the previous picture because it doesn't shine much in visible light. It is a gas that's heated to maybe 1 million degrees Kelvin, and therefore it shines in X-rays. That gas is filling up the galactic halo. It's not the dark matter halo. It's regular matter mixed in, but it's no longer confined to the disk. Can you guess how did it get there and why did it get hot? If it's hot, what does that mean in terms of the kinetic energy? Low kinetic energy or high kinetic energy? Well, what's the relation between kinetic energy and temperature for a gas? Well, that's right. It's proportion between kinetic energy and temperature. So if this gas has high temperature, that means that, those atoms or ions have received a lot of kinetic energy from somewhere. And to spare you the agony of having to answer the question, they got there largely due to supernova explosions, which obviously impart a lot of kinetic energy in the interstellar medium. At the same time, they can heat up the gas. So because the gas has a lot of kinetic energy, it flies high above the galactic disk, just like any gravitational system would work. Okay, so where is the gas? This is actually a picture of the Milky Way from here. And we're in disk, and this is mosaic of near-infrared imagery from the 2-micron sky survey. And almost all of the gas is concentrated in this very thin disk. And then there is this corona, which has some of the hot gas, which really is negligible component by mass, but it's interesting physically. So in studying interstellar medium, you may recall there is this hyperfine structure line of neutral hydrogen that happens when the spin of electron relative to the proton flips. And that tends to happen once every 10 million years or so per hydrogen atom, but there are a lot of hydrogen atoms. And so it tends to be the dominant radiation from the cold gas. Now, if this hydrogen wasn't cold, if it wasn't the temperatures of tens of degrees Kelvin, sometimes it's barely more than microwave background, few Kelvin, do you think that this would be an important line? Let's say with the gas that makes those nice shiny nebulae also shine in 21 centimeter line. Well, since I'm asking the question, the answer is obviously no, because that gas will be first ionized by and large, and second, even if it's not, the energy levels that are populated will be way higher than these, although this can happen at many different energy levels. So the main advantage of observing interstellar hydrogen using this radio emission line is that radio waves zip through the dust clouds as if they didn't exist. And that way, we can actually see throughout our Milky Way galaxy, and same thing, other galaxies. So we can study parts of the Milky Way that are hidden from view in visible light. That, unfortunately, does not include protostellar clouds and protostellar cores. The gas there is actually dominated, the emission is dominated by molecular lines, but that's fine, we can study those as well. So this is picture of the Milky Way, again, from here, in 21 centimeter line. You can see that most of it really is concentrated in the galactic plane, but there is hydrogen at high galactic latitudes as well. Some of it is really near us, and so it's no wonder we can see it up. But other parts of it got there in some interesting fashion. You can see there are kind of arches, almost bubbles. Anybody have an idea where do those come from? If you see something that's probably kind of spherical up there. Well, they too must come from supernova explosions. And a shock wave of a supernova will push the interstellar medium. Even when it's not ionizing, it will still have kinetic energy. And it'll make these shells of hydrogen that just expand for a while before they're dissolved and fall back. All right. So it's interesting to look how different components of the interstellar medium correlate among each other. And the top is side picture of the Milky Way in visible light. And there is obviously big stellar disk and a bulge, but there are shadows in the front, and those are the dust clouds. Now, if you look in millimeter wavelengths, the carbon monoxide, you find out that molecular gas, which you cannot see in visible light one way or the other, goes more or less exactly where the dust grains are. So molecular gas clouds and dust clouds tend to be well mixed together. Also, it turns out that there is a reasonably good correlation between neutral hydrogen, atomic cold gas, and dust emission as well. And the reason for this is, well, just simply gravity, that you have denser spots, say giant molecular clouds, that would attract hydrogen as well. And so there will be some correlation, broadly speaking, but not a perfect one. The molecular clouds are colder, therefore they tend to be more condensed than just generic hydrogen clouds. But in terms of gravity, it doesn't matter. And one last portrait of the interstellar medium. This one is a large-scale picture of most, not entire, galactic plane as seen in the light of ionized hydrogen, the H-alpha line. And you can easily see that there are these bubbles that were produced by supernova explosions. There are some spots it's hotter. Those are the regions where there is some star formation that ionizes the gas.